So thanks for thanks for tuning in today to hear a little bit about what I do at Agranodo and the sister company Geothermica Gallega. Thanks also has to go to the Deep Digital Cornwall Fund from the EDRF, run out of the University of Exeter Camborne School of Mines. So part of that regional development fund contributed to some of the modelling I'll be presenting today. The actual focus of the project was deep geothermal coaxial systems, high temperature, but perhaps that's for another day. So today, as Joe says, I'll be talking about open loop ground source heat pump systems. Is there a zone of optimal performance installation that we should be seeking for such systems? I've referred to it as the Goldilocks zone, and of course, does it exist? Well, hopefully we can find out. Before then, I leap into some of the modeling. I just want to make sure that we're talking about the same technology here. Today, I'll be talking about two types of open loop ground source heat pump system: the unidirectional dump and pump dipole well doublet system. Comes by many names, but essentially this is a ground source heat pump system where we have a dedicated abstraction borehole and a dedicated injection borehole. Also, it's worth mentioning that today I will only be talking about an open loop system that abstracts and injects to the same aquifer. There are other types, but I would suggest that this is probably the most common and simplest form of unidirectional open loop ground source heat pump system. It's probably worth mentioning as well that, of course, we don't for operational reasons, we don't want to put the groundwater back into the source aquifer. That doesn't really help our system. But what it is important for, of course, is regulatory approvals and managing the water resources of the aquifer that we are utilizing. That is, of course, of critical importance to any environmental system. So I wonder whether this will work. Sorry if it lags. It's not an important part really, but it's just nice to have a quick video of what we're talking about when we're talking about these open loop ground source heat pump systems. What do we want on a unidirectional system? Well, we want an abstraction well and an injection well. Here's the injection well. Here's the abstraction well, and we have a dedicated injection well pushing a plume of warmer or colder water into our aquifer. We have our abstraction well, normally up hydraulic gradient, and what we expect to see in a system would be some sort of thermal plume migrating away from our injection borehole in the aquifer and going down gradient. Let's turn that off. What we don't want to see is a thermal interference of our on-site thermal interference of our own ground source heat pump system. I think you may just be able to catch in this this screenshot here of the groundwater model the thermal plume migrating up hydraulic gradient from the regional aquifer and towards the abstraction borehole. That's something we refer to as on-site thermal interference, and that's something, of course, we have to be careful about because we shouldn't expect our abstraction temperature to remain constant throughout the operation of our system. Another thing that we would commonly have to avoid is any thermal derogation of a environmentally sensitive receptor within the aquifer. Here it's a third-party borehole. You can see it's operational, sucking this plume of water towards it, slightly against the gradient of groundwater flow. That's obviously a problem. That might be a temperature-sensitive abstraction. We don't want to be derogating anyone else's protected right, as it's called in England. Comes by many other names in other jurisdictions. But that might be a river. That might be a pond. It might be some other temperature-sensitive receptor that we have in the environment. Obviously, something we need to avoid. The second type of open loop ground source heat pump system I'll be talking about today is a reversible system, so or often called an aquifer thermal energy storage system. So instead of having a dedicated abstraction well and injection well, we have a dedicated warm well and a dedicated cold well. So it's a reversible system. Both boreholes are required to have a pump. And the classic example of this is the snowman showing the winter heating from the building, where we extract water from the warm well, we heat up our building, therefore we have colder water to reject back to the aquifer, and we put that in the cold well. And then in summer, you can see the little sunshine on the right-hand picture there, where we typically have more cooling than heating. So we want to recover some of that cold water back out of the cold well, warm that up by dumping heat from the building into that water and putting it back into the warm well. As I said, that's a classic sort of interseasonal aquathermal energy storage, but there are many different examples. They don't have to be interseasonal. Some of them are daily, depending on the heating and cooling loads, the process that you are serving with the ground source heat pump system. So again, what do we want from a reversible aquathermal energy storage system? Well, we want these bubbles of cold and warm water to form around our cold and warm wells, such that they form a nice, in this modeled example here, they form a nice cylindrical round bubble around our wells, so that we can dump the cold or warm water in the aquifer when we have excess cold or warm water, and we can recover that when we want warm or cold water for heating or cooling. So there's an example there of a system that's working nicely. What don't we want to see when we're looking at aquathermal energy storage systems is the picture on the right, again, a screenshot from one of the models. Here we've obviously got a rather heating dominant system, because of our cold wells have created such big bubbles that they've completely obliterated any warm water that we've been trying to create in our warm wells. So we don't have any opportunity to recover any warmer water. We do have opportunity to recover colder water, but obviously the balance of heating and cooling in a system like this doesn't favor an efficient operation of the heat pump. Or another example of what we don't want from an ATS system on the right hand side there is these bubbles that we've been showing migrating away from your boreholes. Of course, there's always a hydraulic gradient in any aquifer. Water will not be static, only in very exceptional circumstances. So our bubble will be migrating away from our cold and warm wells. As you can see that here, they're all going up to sort of the northwest. And there's, again, a third-party borehole, which we can actually see that the pumping from that other borehole is also affecting the efficiency of our storage of warm and cold water. Not only are we all having migration of the plumes, but we're having this third-party borehole pinching some of our nice warm water. So based on some of that, then the simplest criteria that we have to select an open loop ground source heat pump system, we need a suitable aquifer. We need sufficient space on the site to have the abstraction and injection or hot and cold wells to operate. We need a local regulatory landscape that's favourable to open loop ground source heat pump systems. There are plenty where the injection of warmer or colder water into a drinking water aquifer, for example, isn't accepted. We have examples where, even though the ground source heat pump system returns all the water back to the source aquifer, it's taken to be a consumptive abstraction, and we're not allowed to operate. There are plenty of examples, and it all depends on the local regulatory regime. And of course, because these are complicated systems, we need experienced practitioners. So, very simply put, that is our open loop ground source heat pump Goldilocks zone, where those four factors all contribute. Compare that, if you will, to the closed loop Goldilocks zone, where she's a little less fussy, and we can put a closed loop system, obviously within reason, pretty much anywhere. In fact, I think they want one on the moon when we all move up to the moon. I think they've also talked about having one on Mars. So by the time we're all there, you probably have a closed loop ground source heat pump system, probably in preference to an open loop. But there's no convincing everyone, I suppose. So given the fact that closed loop systems are going to be more applicable, why would we ever want an open loop system then? Well, one example here would be the small district energy scheme that I've been working on in London. On the left-hand side, you can see the district energy pipe in purple, and you can try and squeeze in a few bore fields with closed loop. Obviously, this is in plan view, so you can see the headers. We can squeeze a few in under a car park. We can squeeze a few in under a green area, but essentially, without having extremely strung out closed loop boreholes, we can only have a relatively small number for the size of the system. With an open loop ground source heat pump system on this district energy scheme, we've got the opportunity to put in 4 pairs of boreholes there, so 8 in total, because of course the footprint of an open loop borehole is significantly less. Each one of those can typically be maintained within a basement or under a manhole cover, something like that, and we can have a lot higher thermal contribution from the ground in an urban area in that sort of with the open loop configuration rather than the closed loop. But it's not just urban areas and space, of course. Any Kiwis amongst us, hi Michelle, might recognize the Taranaki there, Matt Egmont in the background. This is a Fonterra dairy we have done a feasibility study for. They've got the space. They're surrounded by green pasture. They could have all the closed loop boreholes they want. But looking at the economics of the system, if we had about 70 boreholes, each of them at 150 meters deep, give or take, we get about the same thermal loads that we can service off just 2 boreholes, 1 pair of open loop wells working at about 16 liters a second. So in this case, even though we have the space available, the open loop boreholes are simply cheaper. It's simply cheaper to drill the abstraction well and injection well once each than it is to drill 250 meters 70 times. The other contributing factor to an open loop borehole being favorable at this site, of course, is a large factory like this has the maintenance crew and the capabilities to own and operate the open loop system. So before I pose the questions that we should all be asking, I'm just going to say, when should we be asking the questions? Here's the Royal Institute of British Architects plan of work that many projects seem to be working on nowadays, both in the UK and internationally. It's at the pre-feasibility stage. Obviously, we should be asking some of these questions about open loop and closed loop. We should be answering a lot of those questions at the feasibility and outline design stage. So really the river stage 1 and 0, 1 and 2, we should have a lot of these answers already quite well defined from the sets of questions that we're about to ask. We certainly don't want to be finding out at the drilling and testing phase, which is river stage 5. We certainly don't want to be finding out at the commissioning handover stage at 6, and of course, critical failures in operation and maintenance during the use of the system is a big banana skin, and so how are we going to avoid the banana skins? A little on the methodology then of modeling, but I won't go into this too much. Obviously, we set up a conceptual model of the site. You can see the geological map there that we've got. We've got to have an understanding of the aquifer. We have an understanding of the geology. We have an understanding of the site setting. We install that into a numerical model. That's a rather fancy looking fee flow model there. A bit more than we would typically do for a ground source heat pump system, but it looked nice, so makes the point. Once we've decided all the driving factors behind the groundwater flow, the controlling factors over heat transport, we put that in numerical model, and then we run scenarios in our numerical model to create predictions. Those predictions are potentially more or less useful than trying to predict the future by looking at the entrails of a gutted chicken, perhaps. And that's the modeling mantra. Predictive modeling can't give you the correct answer. It can only give you an outcome that the potential of which has been minimized for its wrongness. So we have a range of possible outcomes from a numerical model, and that's about that. Every model has to say that once in a modeling talk. So I shall move on from that now. So using the examples that I'm going to be presenting, then these were all set up in the London basin. We can assume a central London site, mostly because, in my experience, the majority of the UK open loop ground source heat pump systems are in the urban area of London. So on the left-hand side, you can see the fairly typical London basin sequence. We've got the Quaternary alluvium over a nice thick aquitard of London clay. We've got Lambeth Group and Thanet Formation over our chalk aquifer, the chalk being a major aquifer. So we have this geological layering. We put that into FeeFlow, which is the green block in the middle. We use a block model scenario normally because we don't want to have to model the entire Cretaceous chalk aquifer. That would be unrealistic. So we simplify that to a local block model, whereby our main interest is to replicate the groundwater conditions, the geological conditions, only in the vicinity of the site, because the argument being that we're only going to have a fairly small groundwater and temperature perturbation within the aquifer locally. So in the middle of that block, we have our boreholes. We put our boreholes into that model. So onto the questions, and the sorts of questions that get asked, the sort of questions I've been asked. It's probably just worth just reading through them. So what are our feasibility assessment questions? How much water can I get from the aquifer at my site? How far apart do my boreholes have to be? Obviously, logistics of urban sites are often controlling factors. How much heating or cooling can I have? I just want as much as possible, please. Is often the question. What orientation should my boreholes be? That's orientation or typically against the regional groundwater flow direction. And then increasingly asked is, should I have a unidirectional or an aquifer thermal energy storage system? So I'll answer these at varying speeds and rates and complexities one by one. But first question being, how much water can I get? In its simplest answer, that depends on the aquifer. How much water can you get out of the aquifer that you have under your site? Obviously, you can't change the aquifer, so it's a function of the sustainable flow that you can get from a borehole at your site. And typically, if you need more water, you add more boreholes. Obviously, that's a simplified answer, but nevertheless, we do start to butt up against other issues such as the thermal loads, the hydraulic interference between boreholes. That's where the complexity comes in. But for now, we can be fairly satisfied that a borehole will do so much abstraction. But of course, the other thing to consider is areas of shallow water tables or shallow groundwater. Traditionally, abstraction wells, drinking water wells, irrigation wells, whatever they might be, are concerned with how much water you can get out of the ground. That's a function of the available drawdown from the water table or the piezometric surface down to a reasonable level within the aquifer above the pump. With our systems, because we're re-injecting, of course, it's often the available mounding, not the available drawdown, that's the limiting factor on our sites. You can only force so much water into the ground. And whilst you might have 50 meters of available drawdown, if you've only got 10 meters of available mounding, well, that's going to limit the rate at which your ground source heat pump can provide water. There are obviously options around that, multiple injection wells for each abstraction well. But essentially, to avoid groundwater flooding, to avoid surface flooding, we need to consider the injection rate as well as the more traditional abstraction rate. How much water? So when I'm asked how much water can I get, the response is nearly always, well, how much water do you need? The top graph there, which looks like a little pixelated QR code or something, that's got each day, each hour of the day vertically, and each day of the year runs from left to right. You may not be able to see it, but there's January. We have week 1 of January here, week 2 of January, all the way to December. And I've tried to line that up with the monthly plot below. But you can see, as you might expect, January to February, March, we've got very much a heating dominant system. This is a fairly typical sort of mixed-use building in London, actual data from a mixed-use building in London. We've got fairly big cooling loads between May and September. We've got some afternoon cooling loads. We've got some evening cooling loads, as well as people start to use some of the facilities differently. Now, if you were to come and ask me, okay, I need up to about 2.5 megawatts of cooling and about 1.5 megawatts of heating peak, well, we might be looking at something in the order of 40 liters a second. And I'm going to say, well, 40 liters a second is a lot of water, even for a big site. But when we start to break it down, when we start to look at the monthly averages in the loads and the average loads and the total loads, we start to see that there is a lot to be said for simultaneous heating and cooling loads. And if we then break that down into what do those peak loads actually look like when you translate that to flow rates? Well, here's a histogram of hours per year of the flow required to service that system that you saw on the last page there. And you can see that about 8,000 hours of that is less than 20 liters a second, 40 liters a second. And most of the year, this 40 liters a second here is only needed 5 hours a year, whereas this is more like 2 liters a second. That's what's needed for most of the year, between 2 to 1.5 liters a second. And that's what we can see corresponding to the average monthly net total heat absorption and total heat rejection rates to the aquifer, which is slightly different from the total heating and cooling loads that we were looking at earlier. So, in fact, I mean, what does this tell us? This just tells us that a peak is a peak. By definition, it's a short duration, high load occurrence. So actually, how much water do you need? Well, your peak is 40 liters a second, but your peak average is more like 2 liters a second. And let's see what we can do then with 2 liters a second. So that sort of hasn't answered the how much water can I get question, other than answering with the question, how much water do you need? The second question, how far apart do my boreholes have to be? Let's take the example that we've got here. You've seen here the plume of colder water going into the aquifer from an injection borehole, and here we've spaced 3 abstraction boreholes, about 50 meters, approximately 50 meters increments from the injection borehole up hydraulic gradient. And to keep the example simple, we're having heating only. So we are only rejecting colder water into the aquifer all year round. What effect does this have? Well, you can see the injection temperature. That's a nice steady 5 degrees C for the duration of this is a 30-year model. Sorry, that's days. That's about 35 years. You can see that the furthest away borehole, abstraction borehole 1, in sort of orangey color there, has, as you might expect, the least impact of any of those. The thermal plume from the injection borehole is the last to reach abstraction borehole 1, and it has the least effect. Abstraction borehole 2, being closer, has a earlier thermal interference and a greater thermal interference. And then, as you would, of course, expect that to continue, we have abstraction borehole 3, which has the greatest impact and the earliest impact. I've added a little bit of seasonality to the injection flow rate, even though the temperature is always 5 degrees C. The flow rate, because it's heating only, goes up a little bit in summer, up a bit in winter, sorry, down a bit in summer, so that you can see annual cycles and what that does. So the answer to the question here, how far apart do my boreholes have to be? Well, if you can tolerate an abstraction temperature of 4 degrees C, then you can see that you could have your boreholes at 50-meter separation, because the abstraction borehole never goes below 4 degrees C. If your heat pump requires a temperature of above, let's say, 10 degrees C, then, well, I'd say you probably need an abstraction borehole that's 150 meters away. The middle example, abstraction borehole 2, if you required a abstraction temperature for your heat pump of at least 8 degrees C, well, you could push your system for about 20 years before you potentially have a abstraction temperature reaching your lower limit of 8 degrees C. So for a heating only system, what's the separation I need on my boreholes? Well, it depends on your tolerance of incoming water temperature for your heat pump. If we have the same setup, then groundwater flow west to east, sorry, injection borehole, abstraction 1, 2, and 3. You can see that over the same time period, we have the injection temperature going up and down, as you'd expect with a balanced heating and cooling load. So we've got summer heat rejection, winter cooling of the aquifer, sorry. And the X and Y axis on these graphs are the same. So the first thing you'll notice is that with a balanced heating and cooling load, the overall impact on our abstraction temperature is significantly less than the impact we have on a heating only system. And the reason behind that should be fairly obvious. The injection borehole is putting in equal amounts of warm and cold water. So the net impact on our abstraction boreholes, whilst we can still see a similar pattern, borehole 1 the most, borehole 3 the most, borehole 1 the least impact, we can obviously see that the overall impact is significantly less. So what can my borehole separation be for a perfectly balanced system? That can be a lot less. And then just a note on changing the hydraulic properties of the aquifer. We've got a abstraction borehole 1 and 2 at distance from the injection borehole. And in these sets of results, I have changed the transmissivity of the aquifer, so the rate at which the ability for water to move through the aquifer, basically, and the hydraulic gradient, or the slope of the water table beneath the site. And you can see that the range of outcomes using reasonable input parameters for both those factors changes the result by about 6 or 7 degrees. In the worst case scenario, we begin to have abstraction temperatures approaching 6 degrees C, but in the best case scenario, well, we hardly have any thermal impact at all. We have perhaps half a degree. So how far apart do my boreholes have to be? Once you admire the graph there, I need a sip of water, sorry. That the separation that you can have depends on the aquifer properties. Now, obviously, aquifer properties are something that we don't know until we've drilled at a particular point. So up until a certain point in a project, we are estimating what those will be. So I guess to try and answer some Goldilocks questions, then where is our favourable zone in green versus unfavourable in red, and everything in between? This is sort of a qualitative analysis of that, and we can see that we have the scenario of a closely spaced boreholes on one side of our chart and distant spacing on the other. I think this just hopefully shows that the unidirectional system, the pump and dump, is more sensitive to borehole separation than the aquathermal energy storage system. The aquathermal energy storage system has a greater Goldilocks zone, if you will, the green zone, than the unidirectional. Now, the reason behind that is because the unidirectional system, operating obviously one way, it's more susceptible to thermal interference than an ATS system, which reverses its heating and cooling. It's got more opportunity to balance those temperatures that we're getting. So we have a more efficient ATS system across a wider range of borehole spacings when the heating and cooling loads are suitably balanced. There's always a caveat with these. The third question then, having hopefully answered the second, how much heating and cooling can I have? Well, I've just done two examples here of a balanced heating and cooling load in the middle, where we can see the ratio of total heat absorption to total heat rejection is about 1:1, where we have, again, through the year, January to December, we have net heating, net cooling. And then if we manipulate that heating and cooling load such that the heating is about 4 times bigger than the cooling, we can see what happens with our simple 2 borehole configuration. So I'm comparing the unidirectional balanced with the unidirectional imbalanced. So this is the heating. This is imbalanced with the heating dominance. So we've got more cold going to the aquifer, and here we've got about the same hot and cold going to the aquifer. These are a bit busy, these graphs, but if we look at the top one, you can see that at the spacing that the boreholes that I gave the boreholes, both unidirectional systems have very small change in the abstraction temperature. So these boreholes are obviously sufficient distance apart such that we didn't get much thermal interference between them. The aquathermal energy storage boreholes have a annual hot, cold, hot, cold, hot, cold, as you would expect, because the abstraction temperature changes when we're abstracting from a cold well and when we're abstracting to a warm well. So based on that top graph there, we would say, well, all boreholes operate within a reasonable range. We have abstraction temperatures that always remain above a couple of degrees C, and we have them that always remain below 20 degrees C. The system doesn't run away in any heating or cooling scenario. We would say that's sustainable. Choose any option. However, of course, there's more to the story than that. If we plot out how much water is needed to be abstracted to satisfy those heating and cooling loads, we can see that the unidirectional systems, there's very little difference between how much that this system had to pump over the 25 years that I modeled it. We're talking what, nearly 2,000 megaliters of water within 25 years. The balanced, when we have balanced heating and cooling loads, you can see that the aquathermal energy storage system works a lot better when balanced than when imbalanced. It's despite the reasonable temperature range of abstraction temperatures remaining within a nice range of temperatures, you can see that clearly the ground source heat pump system here is not doing as well. It's requiring to pump a lot more water to get the same heating and cooling effect in your building. So what we can say there then is that moving from strongly cooling dominant to strongly heating dominant through a balanced system, the unidirectional system has a smaller sweet spot, the smaller Goldilocks zone, yet it's more tolerant to a wider range of heating and cooling than the aquathermal energy storage system, which has less tolerance to the extremes of imbalanced heating and cooling loads. But when we're within an acceptable zone of aquathermal energy storage, it's the Goldilocks zone is probably likely to be bigger. We can get more savings, more advantage with the aquathermal energy storage system than a unidirectional, but not always. Question number 4: how should I orientate my boreholes? So we've got 2 examples here. We've got an injection borehole with the abstraction borehole moving around at various compass points. And with the aqua thermal energy storage system, we've got the warm borehole moving around the set in the middle, and the cold borehole moving around that. I'm not going to present lots and lots of graphs over these, but sufficient to say when the injection borehole is up gradient of the extraction borehole, we have a unidirectional system that works very poorly. That's because thermal interference is much more likely to happen when you have a natural gradient of groundwater taking your thermal plume straight to your injection borehole. So we have a wide range of unidirectional systems working poorly until we flip the injection borehole down gradient of the abstraction well. And that's when we have our Goldilocks zone for borehole orientation. But you can see that the aquathermal energy storage system, again, because it pumps in both directions, it regains some of its regains some of the colder and warmer water that we put into the aquifer. It's less sensitive to the orientation of the boreholes. So we have a wider Goldilocks zone for borehole orientation than the unidirectional. That's because, as we showed earlier, the unidirectional wants to get rid of its thermal plume. It doesn't want to see it again. Aquathermal energy storage system wants to see its thermal plume again. Again, they are, and the caveats of borehole spacings and loads apply. I think it's just the last question, isn't it? Unidirectional versus aquathermal energy storage then. What I'm going to change in the model outcomes here are some of the aquifer characteristics, so the transmissivity and the hydraulic gradient that these boreholes have been installed into. And we have the ideal configuration for a unidirectional system and one of the configurations for aquathermal energy storage. When we have top plot here, a low transmissivity, we have a unidirectional system which works poorly. However, as soon as we get to some sort of tipping point between transmissivity and pumping rate, we have the unidirectional system that has a very large Goldilocks zone. So it's more applicable to a wider range of transmissivity conditions within the aquifer. The aquathermal energy storage system, however, is flipped on that. If we have a very high transmissivity aquifer, we have the opportunity for our thermal plumes to move away much quicker. And so we have a slightly wider zone of unfavorable conditions and a slightly smaller zone of favorable Goldilocks zones under lower transmissivity conditions. If we change the hydraulic gradient, again, we see a flipping of the Goldilocks zones between unidirectional and aquathermal energy storage. With a low gradient aquifer, the water doesn't travel past your site as fast. So the pump and dump, the unidirectional, the plume of water doesn't move away. And we have a problem because we have the thermal interference occurring because your plume of water isn't shifting. And as you can probably conceptualize with the aquathermal energy storage system then, with a very high hydraulic gradient beneath the site, our nice bubbles that we want to create move off. They move down hydraulic gradient as a nice long plume, and we never see them again. So that's one of the, again, that comes with many caveats of how the loads are balanced and how the system is pumped. But essentially, that's true for a doublet single pair system. Okay, nearly there then. Yeah, so to answer the questions then that we asked at the start, how much water can I get? Please, Mr. Hydrogeologist. Well, that depends on the aquifer, but it also depends on the balance of the loads. But also, before you ask how much water you can get, please think about how much water you need. Think about the peaks, think about the average flow rates, think about what you can do to offset any peaks with any of the hybrid systems, insulations, operational, building operational, I mean, not ground source heat pump operation, building operational, thermal energy storage at the surface, all these sorts of things. How far apart do my boreholes have to be? Well, I think that we probably showed that quite nicely depends on the balance of the heating and cooling loads, but also, of course, as was demonstrated, can't forget the aquifer properties about how far apart your boreholes have to be. How much heating and cooling can I have? Well, normally more if they're balanced. The more balanced you can get them, the more heating and cooling you can get, the more imbalanced. You probably have a higher risk of unacceptable thermal interference. What orientation of boreholes is best? That's probably one of the simpler ones. With a unidirectional system, we want to have the injection borehole down gradient, the abstraction borehole up gradient of each other, so that your plume moves away. For aquathermal energy storage system, because it's reversible, it's more dependent on the balance of heating and cooling, how the boreholes are orientated. And then should I have a unidirectional or aquathermal energy storage reversible open loop system? Yes. Ask an expert, which is a cop out. Thank you. Thank you for listening.